Hello and welcome to another video. In this video we're going to be working on extra characters in a string. And in this one you're given a zero index string in a dictionary of words, and you have to break the string into one or more non-overlapping substrings such that the substring is present in dictionary. There may be extra characters in S which are not present in any of the substrings. Return the minimum number of extra characters left over if you break it optimally. So here, if we break it, there is no S, so basically you can break it like this. This is like one way. I guess that's the only way to break it, the best way. So basically this is going to be gone, this is going to be gone, and there will be an S, so you just return one. And this one, so these characters aren't in anywhere, so you can break it like these characters are going to be extra, so you have 3 extra. And the string is 50 characters, there's 50 words in the dictionary, and each word is 50 characters. So this is very similar to there's another problem, like basically the same thing, except it was just a true-false. Can I break up a string into these? And the way to do this is basically the same as that with small changes. So a really convenient way, if you're going through a string to figure out like if it can be broken up into other strings that you have stored, is using a trie. And so basically the way a trie works is it's a tree, and then you can put words into it, and then you can traverse it. So kind of briefly show how that looks like. So let's say I have a trie with LeetCode. Basically a trie, you can think of it as a node is a trie, and then an edge is a character. So we'll have something like a root node, and then if we're trying to put in leet, for example, basically every single trie can have 26 edges to other tries. So if we're trying to put in leet, we'll have like an edge of L that goes to a node, and then an edge of E that goes to a node, and then another edge of E that goes to a node. Actually, I'm going to do it instead of this, so make sure I write the characters. So L, and then E, and then same thing. And then T. So this would be like the trie starting from the root. So to get the word leet, you would basically start at the root, and you'd say like, okay, where does this root go with the character of L? It'll go in here, and so on and so on. And then code will basically go the same way. And if you have two words that are similar, like let's say instead of leet we also have like, let's think. Well, I'll just make up some random, or I guess, okay. So let's say we have a word like less. That's a good one. So S, like this. And the idea is if I'm looking for the word less, I start at the root, and then I compare it to the character that I'm looking at. So I'm looking for an L, the L goes here, then I'm looking for an E, then I'm looking for an S, and then an S. And then so all of these like nodes in a trie are there, and then you have the edges, but you need to know which of these nodes are actually a word. Because let's say I put in the words leet and less, these are the only ones, so these two are the only ones that actually make up a word. So even though I can get to these aren't a word. Like LES is not a word, and so on. And so the way a trie works is once you put in the words, if the word ends at that trie, you can just give it a Boolean value called like isWord or something. So generally a trie has like an isWord Boolean, and then a children array or graph or whatever you want that's going to have the A through Z characters that will connect the trie to other nodes. And then if we, for example, are trying to go through like LeetCode, what we do is so our default can be just not using that character, right? Our default can be like, okay, well, we'll just start here, and then we'll just say we're not going to use this character. So we can make a DP function that's basically going to have like an index, and that's all we need. And then our base, or not our base case, but like our default case of that function, we're gonna store how many extra characters there are. That's what we're gonna store in return. And so our base case can be like, well, we'll just say like the character we're on is an extra character, and we can recurse. So what's going to happen is we'll just like recurse to the next character, and then we'll just return 1 plus whatever this case is. But if we want to traverse this word, we can say like, okay, well, let's start here, and then keep going. And then we can recurse at every single valid word. And the nice thing about this is once you get to a character that is no longer in your try, you can just like break early. So essentially you will start and you will keep going and going and going. And at every single valid word, you can recurse. So here, you basically keep going. And then once you go through these characters, you're going to be over here. And then you're going to try to recurse from this state. So recursing here would be like, there are no extra characters and just give me this thing. And then once you get to this character, though, this is no longer in the try. So once you're here, the S is no longer in the try. So you will just break. So essentially what this is going to look like is you're going to first do the default case of just like saying this is an extra character, let me recurse here. And then once you try that, you're going to say, okay, let me just traverse my try, and every single place there's a valid word, I'll recurse as well. And so you'll traverse here, there's a valid word, you'll recurse to this state. And then once you get to one, you can't go any more down the try. So let's kind of write down our DP function. So our base case is going to be out of bounds, like we're just done with the word, right? Return 0. And then the recursive case is going to be, we're going to have a default of just 1 plus recurse to next character, because that's going to be the case of like this character isn't in our, this character is an extra character, and then if we get something better, that will replace this default case. And then the second case is recurse at every place we have a valid word. And so yeah, so let's say this word wasn't LeetCode. Let's say this word was like leaves or something. The nice thing about this is we can check the characters in the try, and then as soon as we're out of bounds of the try, we can just break. So like this LE is in the try, so we'll be over here. And then once we get to the A, we'll say like, okay, well the current node we're at, we can't go to A, so we're done. We can't like go anywhere else. And so in this case, basically the only recursion we can do is just say L is an extra character and just recurse over here. That's kind of the idea. Our like default recursion is going to be just say the character we're on is an extra character and just go to the next one. And we're also going to try to break at every location, which is fine because it's only 50 characters. So yeah, if you're not too familiar with tries, I'd probably look up like the try data structure, but it's useful for things like this, where you are looking through a big substring and you're checking like are other strings in it. It's a lot more convenient than using like a set or something because it's really efficient. Because you can check if words are in it by just going down the try. And at every single iteration of the DP, we're always going to start at the root of the try, and we'll just compare the characters we're looking at to the actual try nodes. Okay, so let's take a look at the code here. So we're going to make a try, we're going to make a cache, a DP cache, and then we'll have this like function. And so this function is basically going to make a try, and we're going to get the cache, and we're going to take every single, so the other thing is, in order to make this try, you have to insert all of these words into the try. So you start at the root, you put in all these words, and then it'll make all these nodes for you. And it's pretty simple to do, but yeah. So for every single word, you add into the try, and then you just return DP at index 0, and then you just pass in your original string. So let's look at the try first. So like I said, a try is a word value, which means like, is this try an actual valid word? You can do some other stuff depending on what you need. Like if you want to count how many words pass this try, or like how many words ended this try, you can change this from like a Boolean to something else. And then you have a map of children, and the children is just A through Z characters that map to other tries. So the default is it's not a word and there are no children. And to insert a word, you just start at the try, and then you go through every single character and you say like, okay, if that character is an edge from my current try, just traverse to it, and if not, then make that new thing, right? So when you first start and you're putting in like leet, like you're going to be at this and you're going to say like, okay, is there an L in here that goes to another try? If it is, I'll traverse, but if not, I'll make this, and then I will traverse. So you will basically just like keep adding more things if you need to, but sometimes you won't. Like for example, if you put in the word like Lee or something, it's already created, so you don't have to make any more nodes. And so that's kind of the idea. If this edge does not exist, make the edge, and yeah, and then just traverse down. And once you go through the whole word, then whatever try you're at, make that a word. And then you just call the DP function. So the DP function, this is basically just the cache thing. So if this is already cached, return that. If we're on the base case where we're out of bounds, there are no extra characters. This is the base recursion case where we're saying the first character is just an extra character. Let's just try that and then see if we could do any better than that. And then we always start at the root try. So we always start at like the top level here. And then we go through from where we're at to the end of the string. And if we are no longer in the try, like let's say we go through leet and then we try to go to like an S, like there is no more try here, so we can just stop because any characters after that also won't be in here. So if that's the case, we can just break. Otherwise, let's just get the next node. And then once we get the next node, we check, is it an actual word? Because we can only recurse at valid words, right? Like if we're going through this like LeetCodes or whatever it is, we can't recurse at like LE because LE was not a word, right? The only words are leet and less. So basically, if we can recurse, let's recurse. And then just minimize the result. So minimize whatever the previous result plus the recursion. And if you recurse, there are no extra characters to the part like when you recurse, right? Like if your thing is like LeetCodes or something, and you recurse here, well, this whole thing was a word, so there are no extra characters. So the only time there's extra characters is that initial case where we just say like, okay, our first character is extra, and we'll recurse. Then you just save in the cache and return. So, and this kind of format is used in tries. You can have this insert function in the try itself or just write it in here, either way. But pretty much for every try, you need to insert words almost always, and then some other things you can do is like delete words and some other things. But it's pretty straightforward, to be honest, and I think it's pretty useful data structure. And the other thing to think about for tries is whether you want to use tries or like a set is basically like the length of the words and how many words and so on. Because, to put in a try, it takes some time and space and so on. And so depending on how many words you have here and how big they are versus like your initial string, it's going to change if you want to use a try or like just a set or some other kind of thing. So generally try is good when you have a lot of words. Yeah, especially if they're like very long, because then you have to compare your string to the words, which is like expensive. So if there's not a lot of words, if they're short, I'm sure you could do this with like a set as well. That would work as well. Like you could basically, instead of this whole try thing, you can just start at a character, make strings as you go, and just check, is your string in the dictionary? And if it is, recurse. I think that will also pass. So if you don't want to do tries. Yeah. Okay, so let's talk about time and space for this one. So to put words in a try, it's basically you have to go through all the characters of every word. So let's just say, this will be like words times characters in word or something like that. Because you basically have to go through, so let's call this like max or biggest word or something like that. So that's how long it takes to put all the characters in the try. And then for the actual recursive function for the DP, so DP, this index is going to be length of the string. So this will be like plus, let's call that n. And then for every index you start at, you might loop through the whole string, worst case. So that's going to be like n squared, I think. Which is fine because n's like 50 here. So yeah. Yeah, so this is definitely passed with a set as well. I just did it with a try. It just something to keep in mind. If your string is bigger and your words are bigger, that's when a try is going to be better, because comparing strings is going to be like more costly when the strings are bigger. But when they're small, you can kind of do whatever and it'll be fine. Oh yeah, and then space. So like I said, to put every single word in the try, worst case, all your words are unique, and then it'll be basically this. So let's say, for example, your words are like, apple and banana or something. Like they will just go down completely different branches, and then you'll have that many nodes. Like for every character, you'll have a new node. But if you have a lot of overlapping words, then you'll have similar branches. So if you have like al and like aloha or something, right? Like you'll have, or whatever, you'll have like this, and then aloha will just like share, share some of the nodes from the previous one. So best case, you're going to share a lot of nodes. Worst case, all your nodes are unique. Like let's say every single word starts with a different character, then they will basically all guaranteed go down different branches because you'll have like an A branch, a B branch, C, and whatever. So, but worst case, it's this. And then as far as the DP, so once again, the index is going to be unique, and then yeah, I think that's it. So I think it's just like this plus n. I think that's right. Yeah, and then every try can have like 26 children and all that stuff, but that doesn't really matter because that all just depends on how many words you have and like the, yeah, how many total characters you have basically. Yeah, so that's gonna be all for this one. Hopefully it's helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.